Okay, hi. So in this talk I will be talking about timing attacks, as was mentioned before. But timing attacks, they're actually not new. So they've been known for decades. But as Bob Dylan envisioned in the 60s, these timing attacks, they keep on changing. So in this presentation I will focus on how these timing attacks have changed over the last few years, and mainly with regards to web security. So I can mainly skip the slides because of the introduction. Timing attacks, they're a type of side channel attack, which means that you don't directly infer information as you would in a SQL injection attack, for instance. But instead you observe information from your environment and use that information to derive a secret or other private information. So as I've said, these attacks, they've been known for decades, and they have mainly been applied in the crypto world. And there they have been used to retrieve cryptographic keys or encrypted messages. But also to exploit secure connections, for instance, exploiting SSL with the Lucky 13 attack. So the concept of timing attacks is pretty straightforward. So in the first step, either the attacker performs an action or he makes the victim perform an action. And then the attacker measures the time from a certain starting point, which is specific to the system that he's attacking, until a certain endpoint. And well, he measures the time, how long it takes, and then he compares or analyzes this timing measurement. And that's basically all he needs to launch the attack. So in my research, I was looking at examples of timing attacks, and I came up with a new type of timing attack, namely the drunkenness timing attack. So in this timing attack, we will try to determine whether a certain person is drunk or not. And in order to do so, we will go to that person and we will slap him or her in the face. And then we measure the time it takes, so the second step, from the time we slap them until they slap us back. And if this is a short time interval, this probably means that the person is still alert and thus not drunk. And otherwise, it means that the person is actually drunk. But of course, I'm from the academic environment, and I can't just start claiming things without real evidence. So that's why I performed an experiment. So I found myself a test subject who wanted to remain anonymous. That didn't happen. So I went to his place and I wanted to know whether he was drunk. So what I did is I went to him and I slapped him in the face. So at that point, I started my timer. You can see it here. And then you can see that he jumps up quite fast and slaps me back. So he slapped me back in a little over 3 seconds. So to come back to the question whether my test subject, Matthias, is drunk, well, probably not. But of course, at that point, we have just a single measurement. We don't have anything to compare it with. So that's why I did, I extended this experiment and I used the second part. So for the second part, I wanted to have like a predictable value. So I gave some beer to Matthias and made sure that he was drunk. So then again, I performed the same attack. So I went up to him, and again, I slapped him in the face, which is again when I start my timer. And as you can see already, he has a lot of trouble getting up. But in the end, well, he slaps me back. So now it takes more than 8 seconds. So because this value is higher, we can infer that Matthias is actually drunk at this point. So the timing attack worked. And basically that concept, so the concept that I explained before, can be applied to all types of timing attacks. So with the drunkenness timing attack, you measure the time it takes for the person to respond, so to slap you back. And that's related to to how drunk that person is. And the same goes for recovering a cryptographic key or message. So then you measure the execution time of a certain algorithm, and this depends on whether a certain bit of the message or key is a 1 or a 0. And the same goes for the Lucky 13 attack, where you measure the time it takes before you get the TLS error message. And that's related to whether the padding of that message was correct. And using that information, you can use some mechanism to decrypt or to retrieve the plain text information. And it also works with web-based timing attacks. So web-based timing attacks, they're also not new. They've been known for 16 years already, so since 2000, which, well, in the context of the web is a very long time, I think. But well, recently they've been, there have been new types of attacks. So in 2013, Paul Stone presented his work at Black Hat called Pixel Perfect, and he found that after applying certain SVG filters, the rendering time of the GPU would be related to the color of a pixel. So using this attack, he could infer what information was on a certain, in a certain iframe. Also in 2013, Eduardo Vela found that if after a post message, the victim, the victim makes some comparison in JavaScript, the execution time of this comparison is related to the input of the attacker and some secret data. And then there are two other attacks which I think have mainly been known in the academic circles. So there's the direct timing attack, where the attacker directly sends, for instance, login request to the server and measures the time it takes before an error is returned. And using that, he can try to use a smart brute force technique to recover the password of the user. And then there's the cross-site timing attack, which will be the main focus of this talk. So cross-site timing attacks, they're quite different from these direct timing attacks, because here the request is not sent by the attacker, but instead the attacker triggers the victim to make the request. And then the attacker measures the time it takes for this request to complete. And well, because of the way the web was built or created, even for cross-origin requests, by default, cookies are attached to this request, which means that the response that will be returned to the victim will be specific to the state of the victim. So a simple example is if a user is logged in, he will get for the same endpoint, he will get a very large response containing the dashboard or other type of information. And when the user is not logged in, he will get back a small response. And because it takes much longer to download a large response, the attacker will know that the user is logged in or not based on the time it took to download this resource. And you can simply use the error event of an image tag, for instance, to measure the time this takes. And well, this type of attack somewhat violates the same origin policy, because the attacker is able to infer information about a cross-origin resource, which should be prevented by the same origin policy. And just because it's so important, I will briefly go over this same origin policy. So it's one of the main security principles on the web. And basically it states that a website from origin A cannot access any content from origin B. So attacker.com cannot read any content from example.com. But not only the content should be hidden, the length of the responses that are returned should also be kept secret. Because if the attacker has just this knowledge of the length of the response, they can infer already a lot of private information from the user, as I will demonstrate later. So how do these cross-site attacks look like? So here we have our user, which is Robin, and Robin is registered on a certain social network. And the social network consists of two groups, namely the Batman group and the Joker group. Now, on a certain day, Robin is browsing the web, and he goes to a certain website, for instance, a news website, which is not malicious. But this news website happens to contain a script from a malicious advertiser, and this malicious advertiser is trying to show targeted advertising to the user based on whether this user belongs to the Batman group or the Joker group. So the advertiser here will try to determine of which group the user is part of. So just with JavaScript, the attacker initiates a request and measures the time it takes to download it. So you can see, because, well, this user belongs to the Batman group, so for the Batman resource, a large response is returned. So the attacker measures that it took a little over 4 seconds, and then he does the same, but then for the Joker group. And because the user is not part of the Joker group, only a small response is returned. And as a result, it took much less time to download this resource. So in less than 2 seconds, this resource was received by the user. So the attacker then compares the measurement of the first, so for the Batman resource and for the Joker resource, and he sees that, well, for the Batman resource it's much higher, so then he can infer that this user belongs to the Batman group. But of course, this only works in very ideal situations where this user is on a very reliable network, because in a more realistic scenario, the request will go over the internet, so will the response, and there might be network congestions. So in the end, the time it took to download this resource is definitely not reliable, and thus, well, you can see that here it took 6 seconds, which was larger than for the Batman resource. So in the end, the attacker didn't manage to learn anything. So next to the network irregularities from which these time attacks suffer, there's also the limitation when gzip compression is used. So when gzip compression is used, the difference in resource size will be much smaller, which will mean that it will be even harder for the attacker to differentiate between the two resources. And for every measurement, so one solution for the attacker to do here is obtain multiple measurements and then apply some statistics to infer the actual value. But in order to obtain more measurements, the attacker will need to trigger a request with the victim every time. So if there's rate limiting enabled on the web server that's being attacked, well, this attack simply won't work. So in my research, I looked at different types of time attacks. And next to the drunkenness time attack, I also discovered these browser-based time attacks. And these time attacks are quite interesting because they can overcome all of the limitations of the classic timing attacks. And the main reason for this is that the timing measurement only starts after a resource has been downloaded. So no matter what network congestions there are, they don't affect the timing measurement at all. And on top of that, the measurements that are obtained are much more accurate. And even for some of the attacks, well, I will go into the details a bit later, but for some of the attacks, a resource only needs to be downloaded once. So even if there would be rate limiting, well, it won't affect these timing attacks. And also because well, we can cache a certain resource, it's possible to obtain a lot of measurements in a very short time interval. So coming back to the previous example, these browser-based attacks look like the following. So there's the request and response, but as you can see, only after the response has been returned does the attacker start his timer. So these browser-based timing attacks, they exploit a certain side channel. So the attacker will measure the time it takes for the browser to process a certain resource. And with processing resource, this can be done in three separate cases, in three separate things. So either trying to parse a certain resource in a specific format, for instance, as a video, and then the attacker can measure how long this takes for the victim CPU to finish. And then the size of the resource will be related to the processing time of the CPU. And the same goes for storing the resource into the cache or reading it out from the disk. So the attack is surprisingly simple. So these few lines, they're all that's needed to perform this attack. So basically, you create a video element and add 2 event listeners on them. So you add a listener for the suspend event and for the error event. So the suspend event will fire as soon as a resource has been downloaded, and that's when the attacker starts his timer. So he uses the high performance timer, and then after the parsing has been done, the error event will fire, and that's because the attacker is not really interested in knowing the size of a video, but rather he's more interested in knowing the size of a certain HTML response, which is not a video, so it will return an error. And basically then he sets the source of this video to start the entire attack. And this attack can be even improved. So the attacker can add can use the application cache mechanism. So he basically creates this app cache manifest, which says that this resource, so the resource he wants to estimate the size of, will be added to the cache. And for all the rest of the resources, they can simply be loaded from the network. And using this attack, the resource will only be downloaded once with the application cache. And as soon as that has been done, it can be parsed over and over again to obtain a lot of measurements. Another attack we found is a cache storing attack, which is also not that complicated, as you can see. So basically, the attacker creates a request and puts the right puts the right options. So the credentials should be included with this request, which means that the cookies need to be attached with the request. And the attacker also doesn't want to use the cross-origin resource sharing mechanism, so that's why I put this option here. And then basically he fetches this request, and once this is done, he can again start his timer and then place it into the cache for some bogus request. And once it's placed into the cache, he can stop his timer again and measure the time it took to write the resource to the disk. And again, this can be executed multiple times without downloading this resource again, because here the response can be cloned, so you can put clones into the cache over and over again. So how well do these attacks perform? So we again did some experiments where we measured the average time it took to differentiate between two files, and the difference of those two files in kilobytes is on the x-axis. So for these classic time attacks, you can see that for resources smaller than 15 kilobytes, it was not possible to differentiate between these two files. And also here, where the difference in file size was 40 kilobytes, you can see that this thing is missing. And that's most likely that was because there was a small network interruption on our university network, which made that this attack simply failed. And I should also mention that in this graph, the classic time attack is already favored because our university network is relatively stable. So these classic time attacks, they should relatively perform well. But then if you look at the new types of time attacks, so the browser-based time attacks, they significantly outperform these other timing attacks. So, the best performing one is the video parsing one, where you use application cache to store the resource into the cache. And you can see that even when the difference in file size is very small, this attack still managed to differentiate between the two files. You can see that it was much less than 1 second. So that brings me to the demonstration. So in this demo, I will particularly focus on Facebook. In our research paper, which is publicly available, we also discuss several other attacks against other major vendors. Facebook has this ability for Facebook pages to limit the visibility of a certain post. So, for instance, I can target my posts only to, I can make my posts only visible to users who are in the age of 20 to 30, for instance. And when you're trying to access this post while not being part of this group, this target audience, then you will get back a small error message saying that you cannot access the content. So in this attack, we will try to discover the age of the victim. So the first step of this attack requires some creating of Facebook posts, and these Facebook posts are targeted to a specific to users of a specific age or age range. So the attacker creates posts that are only visible to users in the age of 13 until 22, 32 until 4. Yeah. So each post is targeted to users in a range of 10 years. And also to determine the exact age, the attacker creates posts that are only visible to users of the age 13, 14, and so on. So in the actual attack, the attacker will perform one of these browser-based timing attacks. So he fetches the corresponding resources and then obtains timing measurements for them to estimate their size. And based on this size, he will try to determine the range of ages that the user is in. And then lastly, he will repeat the previous step, but then to determine the exact age of the user. So I've made a small proof of concept for this. So here on this graph, you will be seeing box plots that are moving around. And these, when a box plot moves, it means that a new measurement was obtained for that resource, and the resources are located on the x-axis. So there's a Facebook post that's only visible to people of the age 13 until 22, 23 to 32, and so on. So first, the attacker downloads the resources, which is completed quite fast because there's only 6 resources that need to be downloaded. So it's in less than 1 second that this happened. And then he will use the cache storing attack. So the cache storage time is on the y-axis. And then he will start collecting measurements. So as you can already see now, for the second resource, so the Facebook post that's only visible to users of the age 23 to 32, the measurements are significantly higher. So the attacker uses that information to infer that the user is within this age range. And then he will repeat the same experiment. So you can see that for the age of 26, so in 20 seconds, these values are much higher than for all the rest. So in less than 30 seconds, the attacker manages to disclose my age, which I think is quite unfortunate. But even more unfortunate is that these attacks are not just limited to Facebook, but we looked at several other vendors, and basically I don't think we encountered one that was not vulnerable to this attack. So on LinkedIn, it is possible to obtain information about your connections. On Twitter, the attacker can see who you are following, and in some cases, can even infer the identity of the current user. So also, Google allows you to search your own search history, but of course, if you can do this, the attacker can do so as well. So on Amazon, it's possible to look at your shopping history, and the attacker can see what you shopped for and do useful things for that. on Gmail, you can browse your inbox. You can search your inbox for a certain query, and the attacker can also do that, and he can determine whether a certain query returned results or not. And there's other research being done about this, this case in particular, and they show that it has some pretty nasty results. So I hope that by now I've convinced you that these attacks are pretty severe, and I think they should be mitigated. But unfortunately, mitigating these attacks is very hard, and the main reason for this is that the side channels that are exploited by these browser-based time attacks, they are there by the design of the browser and the web in general. So a naive solution would be to reduce the resolution of the timer, but unfortunately that won't work either. So in my examples I use the high-performance timing API, but in fact a resolution in the order of 1 millisecond is already sufficient. And a thing that we as security-aware people can do is to disable third-party cookies, because if the cookie is not attached to the request, the response will not be related to the state of the user. But we know that browsers offer the opportunity to do this, but there are millions, if not billions, of people who are not security conscious, and they just might not do this at all. So there's also a possibility to not only look at the client side, but also try to mitigate these issues at the server side. And there we can make the observation that the cause of these attacks is related to cross-site request forgery. And we can try to mitigate these attacks in a similar fashion. So a solution might be to have a CSRF token on GET requests. Unfortunately, that brings along a lot of other problems, and I don't think it would simply work out of the box. Another promising thing is the same site attribute on cookies, but I won't go into detail there because I think that Mike West will be talking about this tomorrow morning. He authored this same site attribute, so he's the one to tell you about it. So to summarize, when it comes to cross-site time attacks, I think it's unlikely that these will be resolved in the near future. And although it might take a while before these attacks are actually exploited in the wild, chances are that some evil hackers are sitting in this room, and that will all be doomed by tomorrow. So to conclude this presentation, so I've presented some new type of time attack, namely browser-based time attacks. They're quite different from the classic time attacks in the sense that they start the timing measurement after a resource has been downloaded, which makes that they are much faster and much more robust than these classic time attacks. And it's unlikely that these attacks will go away in the near future because the side channels that they exploit, they are there by the design of the browser and the web. And I've shown just a few examples, but you can believe me when I say that many popular web applications are vulnerable to these type of attacks. So in the last part, I briefly touched upon mitigating these issues, but unfortunately, it's very challenging, and we are definitely not there yet. So now I'd be happy to take your questions. Yeah, so the question is whether these attacks apply to stateless applications. I think the simpler answer is no, because, well, if there's no state, then there's no information that the attacker can retrieve. So, yeah, I don't think these apply with stateless.
Next question from there. Have you contacted Google, Facebook, or maybe even the browser vendors?
Yeah, so I've contacted the browser vendors, so Firefox and Chrome. Chrome said that this was I have a slide actually for that. Firefox said that it's not an issue that they can resolve on their own, but they wanted to work together with the people from Chrome to fix it. Unfortunately, that didn't happen yet. The people from Chrome themselves, they said that these attacks are very similar to another report that they received, which is the Spy in the Sandbox, which is about cache timing attacks, but at the level of the CPU, which is completely different from these attacks. So, yeah, I don't think these things will be mitigated by the browser vendors. I also have some responses from the from Facebook and LinkedIn. Facebook discussed it, but unfortunately they didn't plan to change anything. I think that LinkedIn didn't really understand the consequences because, they mainly mentioned that certain content is known to be public, but there's a different thing between something being public and some attacker knowing that the current user has these properties. So, yeah, they're also not interested in fixing the issues.
Next question. Method you show is using JavaScript. So are there any attack methods without using JavaScript?
Yeah. So the question was, are there any attack methods that do not use JavaScript? I'm not entirely sure. Well, I can say that there are none, but we didn't find any yet. But I think that if you don't use JavaScript, then the only way to communicate back to the attacker would be to send requests to the attacker, which is also, there's, I think, some work that was done by Mario Heiderich with some attacks that are based on CSS. Yeah, so if you involve a server, so that's not local on the client side, then you again suffer from the network irregularities and network congestion that might happen. So then I think it's better to remain with these classic timing attacks rather than these browser-based timing attacks if you don't want to use JavaScript for them.
Further questions?
Can you? Okay. So the question was, is this still applicable to websites that are protected against cross-site request forgery attacks? And again, the simple answer is, I think, yes, because cross-site request forgery, protections against cross-site request forgery are typically just on post requests. because, well, with cross-site request-for-re, you only need to protect the resources that initiate some state change. But here you just request something, so you retrieve information, and that doesn't trigger any state change. So in typical applications, I don't think it would make sense to fix those endpoints, well, to mitigate those, to create a defense mechanism for CSRF on those endpoints. So the question was if there's something publicly available to test those issues. Well, our paper is publicly available, and well, as you saw from the slides, the texts are quite trivial. So yeah, you could recreate the same attack in 5 minutes or so. But I do plan to make available some kind of framework where you can test all the different attacks on your one machine against a server that you choose.
Okay. Thanks again, Tom.